Hello there. It's good coming on once again. This is the Academia series. We are continuing our discussion on naming of inorganic compounds. I mean, naming of binary, if I'm to be specific. Naming of binary compounds. Do not forget to subscribe to my channel so that you do not miss any post from me. Now, at the end of this lesson, students will be able to write formulas for simple binary compounds, and they will also be able to write systematic names for binary compounds as well. Now, let's quickly look at our periodic table once again with the ions and everything in it. Remember, I told you that those in group 1, they are all in group 1 because they all have a charge of +1. Those in group 2 have a charge of +2 because their outermost shell has 2 electrons which they can lose to become +2. 3 can lose 3 electrons in that order. Those in 2 minus need to gain 2 electrons to become stable. They gain 2 electrons and add it to their outermost shell to become stable. That's why they are minus. So let's take their charges once again. These charges can also be called the oxidation numbers. Oxidation numbers. That is the charge that the atom seems to carry when they are in a compound. So wherever you see magnesium in the compound, know that the charge on it is +2. When you see sulfur in the compound, know that the charge on it is -2, unless in maybe some other special situations. Chlorine always will carry a charge of -1 as its oxidation state or number. Once again, oxidation state or number is the charge that the atom will carry when it is in the compound. I want you to take note of them. So right now, the charges can also be given another name as oxidation number or oxidation state. Now, let us quickly revise our formation of binary compounds. And here, once again, we have sodium, which is +1, and chlorine, which is also -1. Let's focus on the numbers. 1 and 1 can cancel. So that's why I can write sodium without any numbers on the sodium or on the chlorine, because the 1 and 1 has cancelled. Chlorine, we have 2 here. Chlorine, we have 2 here. We have 1 here. 2 cannot cancel 1. So we say we cross, and then the 1 comes under calcium. So we see calcium 1, which we don't write as 1. Chlorine 2. Chlorine 2. The 2 is now under chlorine. So we see that we have Cl2 here. Let's look at magnesium. 2 here, 2 here. They cancel each other. Therefore, I have this with no numbers shown here. Let's look at hydrogen. Hydrogen, I told you, can behave as +1 or -1. You look at the namings, the special name that we give to each. So here, hydrogen +1. So we have 1 here for hydrogen, 2 for sulfur. 1 can cancel 2. So we exchange. 2 is now for the hydrogen. So we say H2. 1 is for the sulfur, S1, which we don't write as 1. So if you follow the trend, you see what I'm talking about here. Ion is ion. We have 3 here. Oxygen 2. 3 can cancel 2. So let's cross them. Let's exchange them. 2 is now under ion. So Fe2. 3 is now under oxygen. So O3. All right. Now let's look at some more binary compounds. So the same trend. Lithium and oxygen. So I think there's a mistake here. Oxygen should be 2, so we can't cancel, so we cross, so that lithium has the 2, oxygen has the 1. So if you follow the trend, once again, you come across aluminium and nitrogen, 3, 3, 3, and 3, they cancel. That's why we don't put any number anywhere for them. All right. Now, let's come to the real naming of compounds. And let me make it clear that we are using the IUPAC system of naming, or the systematic naming. This is in contrast to the first one that we were using, which we call the common names or the trivial names. The trivial names were just names that were just given to the compounds without any special emphasis on their properties or whatever. So for example, carbon dioxide is a trivial name. So we have an IUPAC or a systematic name for it as we speak. So for example, hydrogen chloride is a trivial name, but some of them we still use it. So some of the trivial names are still being used for some compounds. But for the WIEC system, we are using what we call IUPAC, that is International Union of Pure and Applied Chemistry. We are using the IUPAC, or what we call the systematic naming. And the systematic naming is such that they come with rules. Let's look at some of the rules. Rule number 1 concerning binary compound. It says that you have to identify, because we are talking about binary, from all the examples that I gave you, you realize that the first of the binary compounds is usually a metal. So if you look at the example, most of the examples I've given, this one is a metal or is behaving as a metal or a cation. And the second one is a non-metal or an anion. If you take a critical look at them, metal, non-metal, or hydrogen is not a metal, but he is behaving as a metal or a cation. So cation, anion, or metal, non-metal. So our rule number 1 says that identify the cation part and then the anion part of your binary compounds. After you do that, for example, sodium chloride, sodium is the cation metal, and then we have chlorine being the anion or the metal. Let's look at rule number 2. Now, the cation or the metal, those that have fixed oxidation numbers, I talked about the oxidation numbers earlier, that's the charges on the atoms when they are in a compound. Some of them, the oxidation numbers are fixed. What do I mean by they are fixed? This is because the numbers on them doesn't change. They are always as you see it. So that if I say sodium is plus, sodium will always be +1. If I say calcium is 2 plus, calcium is always, wherever you see calcium, is +2. Potassium will always be +1. So they are fixed. They have only one kind of oxidation numbers. So those with only one kind of oxidation numbers, name them such that their names do not change. We don't add anything to their name. So that sodium will always be sodium. Calcium will be calcium. Potassium will be potassium. We don't add anything or change anything with it. Then we have some few of these cations, however, they have variable oxidation states or numbers, or they don't have fixed oxidation numbers. For example, we have copper 1 and then we have copper 2. So if I say variable, that's what I mean. So you meet copper, sometimes it will have a charge of +1, sometimes it will have a charge of +2. If we are talking about iron, sometimes iron will have a charge of +2, sometimes a charge of +3. Lead, a charge of +1, lead, a charge of +2. So these are the few examples for those with variable oxidation numbers. 1, 2, 3. So whenever you meet them, you have to be very careful. They are named such that because we have to identify which of them we are dealing with, we put, for example, if I'm talking about copper 1, we will say copper and then 1. The 1 is written in Roman numerals and put in bracket or parentheses to show us that it is the copper 1 that we are dealing with, or which is forming that binary compound. And we're able to determine that it's ion 2, which is in the compound. I will show you how to identify that. You also have to name it so that you add ion 2 and then something else, lead 2. So apart from these 3, the rest, you don't add any numbers with Roman numerals in brackets to their name, so that sodium will always be sodium, calcium will be calcium. But when it comes to these special ones, you have to tell us which of them is forming the compound. All right, so let's take some few examples so that when we come here, okay, let me quickly give you the rule number 3. Now for the anion, something different is done to their name. It's such that if I'm talking about chlorine, the last 3 letters is replaced with the word IDE. IDE. So that let's look at the others. If it is oxygen, you see here 4 will go and then IDE will replace that 4. So oxygen will become oxide. Chlorine then becomes chloride. Then sulfur becomes sulfide. We have fluorine become fluoride. Nitrogen will become nitride. Phosphorus becomes phosphide. carbon becomes carbide, hydrogen becomes hydride when they are acting as anions. So remember, we are going to form binary compounds. One part is cation, one part is anion, or one part is a metal, one part is a non-metal. All right, so now, last rule number 4. Some binary compounds are named by first calculating the oxidation number of the cation first. So here, because of how they can form bonds or with other elements, we have to first calculate the oxidation number before we start naming them. So here, we will not name them like the ordinary binary compounds. When it comes to that, I'll draw attention to it. And then we have some special cations and anions. You may see them as a group of elements, but then we consider them as one. For example, we have nitrogen and hydrogen existing together as one unit, and we call this ammonium. We have oxygen and hydrogen also existing together as a unit. We call this the hydroxide. When you meet them, treat them as one. Don't separate the elements. So now let's start some namings. So from what I've given you, so that we go with sodium and that, so that we say sodium as the cation, we don't do anything to it. The anion, chlorine becomes chloride, as I said. Then we have potassium, that is potassium fluoride, calcium carbide, aluminium, nothing is done to it. The hydrogen here becomes hydride. We have hydrogen fluoride. Remember, you see here, the hydrogen was acting as an anion or a non-metal, so the name for it is hydride. Over here, the hydrogen came first, so it's behaving as a metal or as a cation. So we didn't do anything to the name. So take note. We have sodium oxide. We also have magnesium sulfide. Now let's compare them. So all these metals here, they have fixed oxidation numbers. That's why their names were simple without any Roman numerals. Let's compare this with those that I told you have variable oxidation numbers. We have iron 3. Now this is iron 3, so you can see 3 plus. Let's say when it combines with oxygen to form a compound, let's see what happens. From what we did earlier, I realized that 3 and 2 can cancel, so we cross them so that the 2 will count for iron, the 3 will go for oxygen. So which of the ions am I using in this binary compound? It is iron 3. So when I'm naming it, I will say iron 3 oxide. As I said, because this one has variable oxidation number, the one that forms the compound, you have to tell us by writing them in Roman numerals. So this one becomes iron 3 oxide because I use iron 3 in forming this binary. Do not make a mistake and look at the formula here and say this one is iron 2 oxide, which is wrong. Let's compare this with iron 2. This is iron 2 because it has 2 plus, also combining with oxygen. Here, 2 plus and 2 minus will cancel. So let's look at the formula that we shall get. Let's look at the formula that we're going to get over here, and that is FeO. You see, there's no numbers here, and this one is iron 2 oxide. The same way, if you do the calculation, you get this to be lead 1 chloride, 1, 1, so they cancel. So this one is for lead 1, and this one will be for lead 1 chloride. This one, will be lead 2 chloride. Please correct it for me, lead 2 chloride. And this one will be copper 1 oxide. If you do the pairings, this one is copper 1 oxide because we have 2 on oxygen, we have 1 on copper. So when it's changed, the 2 will come here, the 1 will go here, copper 1 oxide. And then this one also give us copper 2 oxide because 2 on copper, 2 on oxygen, they'll cancel. So no number comes over here. All right, so once again, let me go over quickly those with fixed oxidation numbers. You realize that I did not bring any Roman numerals in brackets because they have fixed oxidation number. We did not bring anything there. But those that I told you to be very careful, they have variable oxidation numbers. You have to indicate which of them is forming the compound, and we do so by putting them in Roman numerals. I hope you have enjoyed the lesson. We are still continuing. I'll bring you another set of naming in my next presentation. If you have any question, please do not forget to contact me by writing under my comment section, and expect the next lesson also on binary compounds. All right, see